In this video, we are going to continue looking at the effect of substituents on electrophilic aromatic substitution. In the previous few videos, we looked at each one of these types of substituents in isolation, where we saw that we can have activating ortho-para-directing substituents. These are things that are going to be electron donating groups, so we can have pi donors, which can then donate the electron density through resonance. We can also have sigma donors, which donate the electron density through inductive effects. We have the halogens, which are deactivating but ortho-para-directing, and those have both the inductive effects and the resonance effects. Then we have the deactivating meta-directors. So these can be things that are like carbonyls, which are somewhat weaker, but then we can have these types of things that are also deactivating meta-directors by being electron withdrawing groups. So in this video, we want to look at what happens when we have multiple substituents. So when we have more than one substituent. So two or more substituents exert a combined effect on the reactivity of an aromatic ring. If the groups reinforce each other, so for instance, if they are both activating like in this one, or if they're both deactivating like in this one, then the result is easy to predict. We know that if everything is an activator, then it's going to be more activated. If everything's a deactivator, everything will be deactivated. But if we have a mixture of the two, then it's not always going to be obvious. What we'll see here in a minute is that it tends to be the fact that activators predominate over deactivators. And so something like this, where we have an activator right here and a deactivator right here, this would probably be considered activated because the activators tend to predominate over the deactivators. Then we also want to be able to predict whether something will be ortho, meta, or para-directing. And again, we can just sort of stack these on top of each other. So if we have something like this M-xylene, then we see that this carbon right here and this carbon right here are both going to be ortho or para to this ortho-para director, but they will also be ortho and para to this ortho-para director. So those are going to be highly activated, whereas this one right here that's between the two is less activated, mostly because they are sterically hindered. The two groups on either side of it are going to be large. They're going to block anything from getting towards that carbon. So it's going to be this carbon right here and this carbon right here that are most activated. So when we do a reaction, we'll get something like this as the major product, where we now add this group right here, which is ortho to this group and para to this group right here. So that's going to be the major product in that one. Whereas if we have something like this, now we see that this carbon right here and this carbon right here are going to be ortho to this ortho-para director, but also meta to this meta director right here. And so adding onto one of those carbons is going to be the major product. In those cases, it's easy to predict because both the ortho-para directors up here are guiding towards the ortho and para positions. And when we have an ortho-para director and meta director working together, then if we have carbons like these that are ortho to the ortho-para director, but also meta to the meta director, then we can see that everything is working together. But if we have groups that are working at cross purposes to each other, then we're going to get a mixture. So we have on here these two ortho-para directors that are now adjacent to each other. So any other carbon in here is going to be ortho or para to one of them and meta to the other. And so that means that one of them is going to be directing it there, the other one is going to be directing it away from there. So when we have two groups like that and they're both in a tie with each other for how strongly they're ortho and para directing, then what's going to predominate are the steric effects, where now we see that adding a group right here is going to be meta to this group right here, but para to this group right here. Or we can add it right here, where now it is ortho to this group right here, but meta to this group right here. But we see that this one is going to be more favored, and that's because we are adding to a carbon that is not next to one of these two groups right here. And so they are not sterically hindered from adding there. And when there is a conflict between an activating group and a deactivating group, it tends to be that activating groups are going to predominate. So the rule of thumb here is that activating groups are usually stronger directors than deactivating groups. In fact, it's helpful to separate these substituents into 3 classes, from the strongest to the weakest. So the strongest here, so powerful orthopara-directors that stabilize the sigma complexes, are going to be predominant. So that's going to be things like OH, or if we have an ether group, or if we have an amine group, those are going to tend to be the strongest directors. So if you have one of those, then the reaction is going to proceed with those as the directors. The number 2 spot here, so moderate orthopara-directors, such as alkyl groups and halogens, if one of those is the strongest directing group, then those are going to predominate. Then all the meta-directors are going to be the weakest. So again, we see here groups like these are going to be the strongest when determining where the regioselectivity of the reaction is. Then we have these as the intermediate, then these are going to be the weakest right here. So what we see is that if 2 substituents direct an incoming electrophile toward different reaction sites, the substituent in the stronger class predominates, where this one right here is the strongest, this is the weakest. So if we have one of these, then they are going to predominate over the other 2. If we have one of these and one of these, for instance, then this one is going to predominate over this one. If we have substituents in the same class, then we are going to get mixtures. So for instance, the methoxy group is a stronger director than the nitro group, and substitution occurs ortho and para to the methoxy group. So if we have our methoxy group right here, then a nitro group right here, what we're going to do is add onto probably this carbon and this carbon, because this one right here is going to be sterically hindered. So this carbon right here and this carbon right here are going to be the most activated. So our major products are going to be adding it right there or adding it right there. And again, that's because this methoxy group is our ortho-para director and it's going to predominate. So the products are going to be adding it ortho or para to that group right there. Again, this carbon is sterically hindered, so that one is a lot less likely to get added to. As kind of a quick guide to figuring these out, I found this on Wikipedia. So the most activating substituent usually controls or the less activating one. So for instance, if we have this amine group here, then this alkyl group right here, then the amine is the stronger activator, and so that one is going to win out over the weaker activator, the alkyl group. And so we're going to add ortho to this amine group right here. Whereas if we have something like this, where we now have 2 deactivators, what we see is this stronger deactivator right here is going to win out over this weaker deactivator, so these are going to get added meta to this stronger deactivator right here. Then number 2 here, in particular, the ortho and para directors control over the meta ones. So again, we see here, if we have this ortho para director, then it's going to add ortho and para to it. And over here, where we have this meta director and this ortho para director right here, we're going to add ortho and para to the ortho para director. Number 3 here, when multiple substituents are comparably activating, steric hindrance dominates regioselectivity. So if we have something like this where it has this tert-butyl group on it and this methyl group, both of those are activating ortho-para directors, but we see this one right here is a lot larger, so it's going to have more steric hindrance, and so we are going to add ortho to the smaller group right here. So that's where that's going to add. And number 4 in particular, the position between 2 substituents, each meta to the other, reacts last. So we see here we have this ortho-para director right here, and this ortho-para director right here. This carbon would be meta to both of them, and so that one is going to be the least activated. And so now what I'm going to do is go through a few examples of these, and we're going to look at where the regioselectivity is likely to be. I would encourage you, I'm going to do all of these in pairs like this. If you are trying to learn this, to pause the video, try to do it by yourself first, and then watch what I do for the solution. So in this one, what we see here, we have a methoxy group on the top of both of them. Then down here, we have this alkyl group. Over here, we instead have a halogen. So what we want to do is classify each of these groups as either activating or deactivating, and then either as an ortho-para director or a meta director. What we see is that the methoxy groups are strong activators and strong OP directors, where then the one on the left here, we have the alkyl group that is an activator and an OP director. Then over here, we have the halogen that is a weak deactivator and is an OP director. And so what we see is for the one on the left, we are likely to add to these two carbons here because these are ortho to the stronger ortho-para director. So the stronger one is going to predominate over the weaker one. Similarly, over here, they're both ortho-para directors, but this is a stronger one than this one, so the methoxy group is going to predominate over the halogen, and so we will add ortho to this stronger ortho-para director. The next one, we have the same substituents, but now they are meta from each other rather than para from each other, and so we still have the same groups on here, and then we'll see on the one on the left here, we're mostly going to add onto these two carbons, because on those ones, they are ortho to our ortho-para directors. We might get a small amount on that carbon, but again, because it is sterically hindered, we're probably not going to get very much activity there. Then over on this one, we're still, again, going to add mostly to those. Both groups are ortho-para directors, so adding ortho to them is going to predominate. And so we see that each of these two spots here on both of these are ortho to one of the groups and para to the other. And so those are going to be the most predominant spots. Again, we might get a very small amount on that carbon, but again, because it is sterically hindered, it's not very likely. Then if we look at it with the same substituents, but now they are ortho to each other, what we see is on this one on the left, we are going to get activity at these carbons. We can see I tried to modulate these based on the size of the arrow, that the ones that are ortho and para to this methoxy group are going to predominate over the alkyl group right here. We might still get some substitution here at the ortho and para to the alkyl group, but the methoxy group is going to predominate over the alkyl group. Similarly, the methoxy group will predominate over this halogen as well. Then we have these two molecules here, where the one on the left, we have an activating group up here and an activating group down here. So we have this methoxy group and this amine group. Both are activating and both are ortho-para directing. Then on the right here, we have the methoxy group, that's the activating ortho-para director. Then we have this acetyl group over here, which is going to be deactivating and meta-directing. So we see that on the one on the left here, because these are equally strong activators and equally strong OP directors, we are going to get a mixture of substitutions at each one of these carbons. Where the one on the right, it's pretty much going to be all at these carbons, because we see these are ortho to our OP director and they are meta to our meta director. So these are going to be the carbons that gets added onto here. Then if we have these same substituents, but now they are meta to each other, what we see is the one on the left here, we're mostly going to get addition at these two carbons here, because now if we look at this one, for instance, it's ortho to this ortho-para director and it's para to this ortho-para director. So those are going to predominate. We might get a very small amount at this carbon, but again, that one is sterically hindered, and so we're not going to get very much activity there. Then the one on the right, we see that we're mostly going to add onto these two carbons here, because this strong OP director is going to predominate over this meta director here. And so adding two carbons that are ortho or para to this ortho-para director is going to predominate. We might get a very tiny amount of activity here, but again, that's going to be sterically hindered, so there is not going to be very much going on there. Then if we look at these same substituents, but now they are ortho to each other, we see that we now are going to add onto these carbons, so we're going to add onto the ones that are para to one of these ortho-para directors. We see that if we add onto here, it's para to this one, but it's meta to this one, so it's slightly less activated, but it's still going to be predominantly on these two carbons. The reason for that is these two carbons right here are closer to these substituents, and so there is these steric effects that are going to block reactions at those two carbons more than at these two carbons. Then if we look at the one on the right here, we are mostly going to add to this one because it is para to this ortho-para director, but also meta to this meta director. And this one right here, this is ortho to this ortho-para director, and it is meta to this meta director. But it's also closer to the substituent, and so this one is sterically blocked, and so that's why I made this arrow bigger than this one right here. Then if we look at it for these two substituents here, where on the left we have the same two substituents, but they are meta to each other, other. Then on the right, we have the same substituents, but they are para to each other. What we see is that we have this alkyl group, which is an activator and OP director. Then we have this nitro group, which is a strong deactivator and M director. But remember, our OP directors predominate over the M directors. And so on this one, we are going to get reactions that are either ortho or para to our ortho-para director. Similarly, over on the right here, but now these two carbons are ortho to our ortho-para director, but also meta to our meta director. And so those are going to be highly selected for. Then if we look at something that has two M directors on it, what we see is we have these are strong deactivators, these nitro groups, they are M directors, and this carbonyl group right here is a deactivator and M director. So on this one right here, this is going to be meta to both of our meta directors, and so all of the reaction is pretty much going to take place on that carbon. Whereas over here, we see that we have the stronger deactivator up here, and then the weaker deactivator down here. So they're both M directors. These two carbons right here are meta to the nitro group. These two are meta to our acetyl group. So we're going to get reaction on all four of those, but the stronger deactivator is going to predominate. So we are going to get more reaction on these two carbons right here. Then if we look at this for something like this, where we now have two activating groups on it, they're both about the same strength of activating groups. They're both alkyl groups, but now one of them is very large, the other one is a lot smaller. So now we are looking mostly at the steric hindrance here. So like I said, they are all activators, they're all OP directors, but what we're interested in here is the steric hindrance. So we're going to get mostly reactions at this carbon right here on this one, because it is para to this ortho-para director, and it is also not next to this large group right here. We see this carbon and this carbon are both close to this large group, so they are sterically hindered from getting at those carbons. So this is going to be the carbon where most of the reactions occur. You can see I made this arrow slightly bigger than this one. This one is sterically hindered by this large group, but this one is sterically hindered by both the large group and this other group over here. So we are not likely to see much reaction at either of those, but probably more so at this carbon than at this one. Then if we look over at this one on the right, we see that we're going to get reaction mostly at these two carbons. Those are both ortho to this ortho-para director right here, and they are not blocked by this large group right here. So we might still get some reaction at these two carbons, but not nearly as much as at these two, because these two are a lot more hindered by being next to this large group than these two are by being next to this smaller group. And finally, the last one we'll look at is this one, where now we see we have the alkyl group at the top, and now we have this CF3 bound to it. What we see with this CF3 is that the fluorines are a lot more electronegative than the carbon, so they're going to pull electron density away from the carbon. So the carbon is actually going to end up with a partial positive, and so the CF3 is actually going to be an electron withdrawing group, which means it will act as a deactivator in this case. So these will act as deactivators. We'll see on this one on the left, we're mostly going to get reaction at these two carbons here. One of them is ortho, one of them is para to our OP director, where OP directors, again, are going to predominate over M directors. We might still get a very small amount of reaction here, but that one is sterically hindered, so there is not going to be much there. So these two carbons right here are where most of the reaction is going to occur on that molecule. Then if we look at the one on the right here, what we see is pretty much all of the reaction is going to happen at these two carbons. They are ortho to the ortho-para director and also meta to the meta director. And so pretty much all of the reaction will be at those two carbons. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.